thank Mr. Shailendra for setting the stage right, talking about the permanence of carbon sequestration in biochar concrete. So what I'm going to discuss today is how to design a biochar-based cementitious composite and what are the different parameters we look at, including carbon storage and also other engineering properties. Because just talking about carbon sequestration is probably not adequate in the context of building materials or any materials. We also have to look at its implications on the engineering properties, and other performance, right? So that is, the agenda. So before we dive a bit deep into this topic, we first have to understand the kind of challenges we're dealing with, and one of that is decarbonization of construction materials as a whole, right? And that's where this concept of embodied carbon comes in, which is basically the total carbon that goes into manufacturing any material, raw material extraction, processing, and so on, right? So what you see here is the total carbon is a summation of embodied carbon and operational carbon. And as of today, if you take the ratio between these two factors, which define the total carbon footprint of building, it is about 25-75, 25% contributed by embodied carbon, right? But the United Nations have predicted that in next 2 to 3 decades, this ratio may completely change, going up to 50:50, about 1:1, right? And the reason being is that we are overly dependent on mined materials. We are not very much into biomass-based materials, into certain challenges that exist. And now mined materials are becoming scarce every day, like sand, for example. We have a very severe scarcity of sand in most states of India, right? So we need to search for alternatives. The same goes for cement and so on, right? So now the challenge with embodied carbon is that if you see on a temporal scale, most of the embodied carbon will be accounted for even before the occupancy of the building, right? And that is the major share. And throughout the lifespan of the building, you have very little scope to mitigate embodied carbon. You can mitigate operational carbon through different strategies, decarbonizing the grid, increasing the dependence on renewable powers and so on. But embodied carbon is something which must be addressed well before the building design is conceived, right? So that is where a lot of planning, a lot of strategic thinking comes in, and there are different ways that one can, of course, mitigate it. So we have to understand that if we look at the carbon sink, we call it like concrete as a carbon sink when we have biochar in it, but now nature is the biggest carbon sink, right? And this is the carbon balance, right? What you see in front of you, like the ocean, it can sequester about 2.8 gigaton of carbon. You have additional carbon sequestration in the soil, but then there is always a disbalance between how much we are sequestering on an annual basis and how much we are emitting, right? And that is mostly from the fossil fuel. So we must devise strategies. For example, we are clearing forest areas for new infrastructure development. We are losing our long-term carbon storages. So now can we extend this carbon sequestering strategy to concrete, right? So that our future cities can actually be low carbon, or at least try to be as carbon neutral as possible, if not carbon negative. So the challenge is we consume a lot of cement in India and internationally. And if you manufacture 1 kg of cement, you are emitting about 0.8 to 0.9 kg of CO2, right? And most of it comes from this simple reaction, what you see. This is the calcination of limestone, right? And it emits about 44 grams per 100 grams of limestone, that is what. And the rest of the emission comes from your energy, from transport, and etc. Right? So to capture the CO2 back, it is extremely challenging. You can capture part of it back, but not in its entirety, right? So you always have a shortfall between how much you can sequester and how much you are emitting, right? And about 12% of the total energy-related emissions accounted for by the manufacturing and construction sector, right? So there is a huge need to look at different options that we have in hand to decarbonize the building and construction materials in India, keeping in mind that by 2070 we have pledged to be a carbon neutral economy. So this shows that from 1930 to 2013, about 80 years. So what kind of shortfall we have now, right? So what you see in green is basically the uptake of CO2 by carbonating materials. So for example, you take any alkali material like calcium hydroxide, lime, for example, cement, for example, right? So it can sequester about 4.5 gigaton per year, right? And then we're emitting about 10.4 gigaton from cement emission. So if you subtract the two, you get a net emission of 5.9, which is unabated, right? And this is something we need to address, or we need to bring it close to the neutral line for decarbonization. So I saw something very interesting published just, I guess, couple of months back in the journal called Science, one of the premier journals. And probably this is the only article in a very premier venue talking about different strategies to decarbonize building materials. And you can see the first two rows, which says carbonatable cement and carbonate-based aggregate, whereby you are basically reacting these materials with CO2 and you are sequestering in the form of minerals. For the aggregate, it is very encouraging because you see that global annual production of the aggregate is also very large. That is the bar in blue. But if you look at the quantum of CO2 that can be sequestered, biochar is actually much more compared to what you can do by carbonating cement and aggregate. That is the third one. There is about 1.1 to 3.12 kg CO2 per kg. But the challenge is that the application of biochar in building material now is still at a very, very nascent stage, at a very small scale. The total amount of abatement you are having is actually less compared to other CO2 sequestering measures. And also to make CO2 sequestered through active chemical reaction, it also costs a lot of energy and a lot of money, which is shown in the table here. But you can see that is the total cost, including capital cost and operational cost. So biochar has a strong potential to abate a lot of CO2 emissions, but we also must upscale its implementation in cementitious building materials. So this is one life cycle study, again a couple of years back, that compares what kind of CO2 emission or greenhouse gas emission reduction one can have from different applications of biochar, right? And this is based on water hyacinth biochar. And what you see is that if you take soil enhancement, that is the first one, and the second one, you have about minus 313 or minus 706 kg CO2 equivalent of reduction. And in concrete, it is in between the two, about minus 550, 570, right? Which is also very encouraging, right? Because to make 1 ton of concrete, I am emitting about 400 to 500 kg of CO2. So if I can abate this much, I am going very close to carbon neutrality. But that being said, it is very important to acknowledge that if we say that we are producing biochar for the sake of preparing it, we are actually not carbon neutral. We are emitting more emissions. But if you are using all the co-product of the pyrolysis, for example, the bio-oil, the biogas, and the waste heat, then the entire process can be carbon negative, right? So this is the assumption based on which all these calculations were made. So I won't go into details. I mean, I'm sure you have heard enough of it in the last 3 days. Right. So when I started this research about 10 years back during my PhD, the question that was that we often encountered was that why do you want to mix charcoal in concrete? Of course, I mean the people who asked did not know the difference between charcoal and biochar, because see the properties of biochar is overly dependent on how it is made, from what feedstock it is made, right? And to make it compatible in concrete, you need to attain certain physicochemical properties. So what we did is we took inspiration from soil scientists, because biochar as a soil enhancer has been around for many decades. And for soil enhancement, you need certain properties. For example, water holding capacity, right? Then you need to make room for soil microbes and so on. And in cement, you need the very same properties. Right? Why? Because in cement, you have a reaction called hydration that forms the hardened product. And for that, water retaining is very important. Right? And without water, the hydration cannot proceed. Right? So biochar can actually be used as a water retainer in cementitious building material, which can improve its properties. So that was a sort of, I would say, cross-disciplinary learning that we had when we started off. So now if you look at biochar under a microscope, you will see this sort of structure, very porous structure, right? But you can also size it to the range that you want. It's very easy to grind. And you can get a wide range of property like you see in the table, the pore volume, carbon content, etc., which also tells you how much carbon you are effectively sequestering, that can widely vary, right? So it is very necessary to understand the role of feedstock, the role of preparation conditions, and then all of these are going to influence the performance of the final composite products, right? But one thing I must say here is that if you look at this image, you see a lot of pores on the surface, and here you don't see many, right? But we must not think that these are not porous. These are highly mesoporous materials, and these are very active in CO2 capture through the absorption process, right? Why we can't see the pores is because of the resolution of the microscope, but you can of course do a lot of gas absorption study to find out the range of porosity and etc. Then of course you can do a lot of analytical study to find out the composition of the biochar, but particularly this is very interesting. This is from a study by Focus 2010, a little old, but then what it did is that it compared a lot of data on stability of biochar, and based on soil condition he predicted the half-life or the stability of the biochar over time, right? So if you look at this, I have marked 2 points here, that is from the woody feedstock. At 300 degree and 500 degree the biochar is produced. What kind of stability one might experience depending on the carbon content and oxygen to carbon ratio. This is quite encouraging, taking into account what kind of half-life it has. But in cement the condition is highly alkaline, unlike soil, right? So this might vary a bit because of the difference in condition, and there is a huge scope for study into this aspect, long-term study, to understand the stability of the carbon in the biochar, to understand the permanence of the carbon in biochar when exposed to high pH. So now discussion of biochar in building material is not complete without talking about this particular example. This is from Ithaca Institute in Switzerland. I would say they were one of the early adopters, or at least at a prototype scale, that demonstrated that biochar cluster can be used as a very good humidity controller in buildings to control the air humidity and so on. It's a fantastic example, definitely not structural concrete, but at least a first step in the line of building materials, biochar-based building materials, right? Then there has been, some efforts in biochar-based concrete early in 2012, before my first article came. So that is one such study which showed that if you have biochar from wood and you add 5% of it in concrete, you can have a slight increment in strength, what you see here, right, on the bottom hand. But then the problem is that if you mix too much of biochar, you are going to have a lot of water absorption, and because of that the flow reduces. Flow is nothing but the consistency of the concrete, how workable it is, right? So there is a huge scope to even tune the biochar further so that we get good consistency without losing too much water from the concrete to absorption. Right? So these are the gaps that were existing when I started off with my research. So these are the questions that we set out to answer, is that, how does biochar influence the carbon storage, that's the carbon sequestration capacity, and how does the carbon sequestration going to affect the long-term durability of cement-based composites. Then can we make biochar-based lightweight materials, for masonry application, for bricks and so on, and can we even activate the surface of biochar for higher CO2 capture and tuning certain properties, right? So I'll just give you some snippets from my research, not going too deep into the science, but at least some applications you probably understand. So we had this hypothesis is that if we develop a biochar-based lightweight material, like a lightweight brick, for example, we are creating a lot of diffusion channel for the CO2 to penetrate. And when you have a lot of these pore spaces inside the material, you are creating cradles for CO2 sequestration. These are the additional spaces, right? And then you can, of course, improve the properties because some of these pores will be filled with the calcium carbonate by reacting of the CO2 with the calcium-based materials in the matrix. So how does biochar play a role here? Biochar also creates some of these diffusion channels for higher penetration of CO2. And that could result in higher carbon capturing capacity of these building materials. So this shows an example. So this is a biochar that we made in the lab, highly porous structure. But there are two aspects to it. One is that some of the pores can be filled with hydration products, but not all, because it depends on the sort of functional groups that are present. And these unfilled pores can be channeled for diffusion of CO2. And the second is that around the biochar, you'll see a small interfacial zone it happens in all composites. When you have two different materials, two different properties, densities, etc. And even these porous zones can give pathways for reaction of CO2 and also densify the material, right? So these two combined should actually improve the CO2 capturing capacity compared to a solid block, of course reducing the dead load as well. So what we did is that we put our composites inside a controlled CO2 incubator, and the study that we are currently doing is that we are using a simulated flue gas that is from the cement, cement kilns, and we are injecting this flue gas into a chamber with some sensors, and then we are measuring how much of CO2 the material is absorbing, right? So now the implication is that when you take such flue gas for direct flow into the chamber for a pilot scale study or for a commercial scale study, you don't have to separate CO2 from the flue gas. You can directly use as it is. Because separation costs a lot of money, costs a lot of energy. That was the whole thinking behind that. So I won't go into this, but let me explain what these two charts mean. Is that the chart on the left, the plot on the left, on the y-axis, it shows how much of calcium carbonate is formed, and on the secondary y-axis, it shows what is the net CO2 uptake, and that is shown in the green circles that you see here. Right? And the plot on the right, it shows that if I use the same material but of different density, what kind of CO2 uptake I get at different time intervals. And if you compare the two, you will see that the net CO2 uptake is always higher in the lightweight masonry block compared to the solid block, right? And that is because of higher penetration and higher reactivity of CO2 in this material compared to this material. So it is possible to make lightweight bricks, and it is increasingly used in building construction nowadays, that you can have higher net CO2 uptake and offset some of the embodied carbon of the material in this process. And then we quantify that if we take a real scale brick of certain dimension that is used in the Indian market, let's say, of a 300 mm by 500 mm and I think 100 mm, 200 mm of thickness, what is the quantum of CO2 uptake it may have, right? And this shows a pretty interesting result, is that with biochar, which is this cluster of plots, it shows a substantial increment compared to the lightweight bricks without biochar, right? And that is because of higher carbonate mineralization that formed, that was shown in the previous plot, and higher depth of carbonation that we also got from the biochar based materials. So there is a huge potential that we can increase the amount of sequestration by using biochar impregnated lightweight blocks. And we did a lot of these strength studies, which also shows quite a bit of improvement in terms of strength, about 20% with biochar. And part of it was attributed to the fact that we had a lot of hydration product that densified the pores and also sort of acted like an anchorage between the two materials, the cement and the biochar. And we also had a reduction in shrinkage, because that's a big issue when it comes to lightweight porous materials. You have a lot of shrinkage, and due to that you have a lot of cracking, early age cracking in the material, right? So we had quite a bit of reduction in shrinkage compared to the control case, that is without biochar. And shrinkage is actually affected a lot by the porosity of the material. So when we are reducing the porosity of the material to the deposition of the calcium carbonate crystal, that leads to lower shrinkage. So this is another study we wanted to look into depth, is that if we make a high strength concrete and we have a high strength biochar concrete, how do they perform? How do we compare in terms of the elevated temperature performance? The reason being, if you take a high strength material, for example like a shear wall, and there is fire in the building at 550, 600 degrees, which can reach within a matter of 5 minutes or 10 minutes, you can have this sort of falling failure of the walls. And this happens because the material is so densified, it becomes a pressure cooker, right? And the steam cannot go out. Concrete contains a lot of water, the steam turns, water turns into vapor, and it leads to the spalling of the concrete. It's a very devastating failure, right? And what happens during or just before the spalling is that all the cement hydrates that are formed, all the chemical reaction products that are formed, are actually decomposed by 550 degrees, right? And the concrete loses its strength. And that is the reason you have such sort of failure. So can you at least mitigate this failure, if not prevent it, by using biochar as an additive? So again, we took a woody feedstock and we added different percentages of biochar to the concrete. Very low percentage because it is a very high surface area material, 1% to 2%. And then we took a conventional admixture from the market. So for example, silica fume, right? Silica fume is used for preparation of high strength concrete very often. So then we wanted to compare that if we have 10% silica fume, which is by volume similar to 2% of biochar, how do they compare against each other, right? And this is the temperature time curve at 300 degree and 500 degree. We increased the oven temperature, maintained it for an hour, and then we took out the sample and looked at the different properties. So what we measured is the retention in mass, or the loss in mass, and the loss in strength. So this is shown in the left-hand plot, the kind of mass loss that we have. So you will see, interestingly, compared to plain concrete where there is no biochar, the mass loss is actually much higher compared to the biochar concrete. Coming to the strength, you see that the strength reduction is also much lower in biochar concrete compared to the silica fume concrete, which is actually shown here, right? So, or even compared to the plain concrete. Then we were very, kind of astonished, and we wanted to understand what causes this change or this improvement in mass and strength retention after elevated temperature exposure. Then we did some porosity studies because strength is always linked to certain levels of porosity. So we kept the samples in water and we tried to find out what is the rate of water absorption that you have. Does it correlate with the strength loss? And what's the sort of water penetration one will have due to the cracks caused by the fire, caused by the high temperature. So what you see here is that in case of the plain concrete or even silica fume concrete, in some cases you have a total penetration of water, meaning the cracks are much more extensive compared to the biochar concrete, which is little blackish in color, however, but the water penetration depth is much lower compared to this case, which means the extent of damage is much mitigated in biochar concrete compared to normal concrete. Then we went one step down, we looked at some of the images from the microscope and we compared the scenario before fire and after fire. So the first row of images show the microstructure before elevated temperature or fire condition, where you see more or less densified precipitation of the gel around the aggregate particles in all cases, right? But after exposure to elevated temperature, you see a lot of changes to the interfacial property between the aggregate and the paste. And in case of silica fume, the paste sort of completely disintegrated, which you can see here, a very grainy like material, unlike the blanket like material which you see here. So there is quite a bit of change due to the presence of silica fume. But when we look at the biochar concrete, we saw something very, very unique, very different, right? So what happened is that if we take a biochar particle, we saw that the particle is actually damaged, but the cement paste around the particle is still more or less intact, which you can also see here, that the cementitious paste which is deposited inside the biochar has cracked, but around the biochar it has remained more or less similar, right? Which means that this sort of particle can actually give way for the steam to be evacuated, keeping the main structure of the concrete intact, right? So it's sort of a pressure release valve, how it behaves in case of the biochar concrete, right? And it mitigates the damage, right? And this is also explained here, so how the tensile strength and the pressure varies with change in temperature, which is mitigated in biochar concrete. So one more study, I think, maybe another 5-6 minutes I'll take. So like I mentioned that in case of soil, you need water retention to retain the nutrients, to retain the moisture. In concrete also you need that. And we call it by a special name, internal curing effect. And I'm happy to say Dr. Anjana Dikshit from Civil Engineering is here, and we did a joint investigation a few years back. Very, very interesting results. So I think you can also discuss with him, about this. So why we wanted to look at it is that when you have a freshly laid concrete pavement or a wall or anything, you have a lot of this shrinkage cracks that happen. And these shrinkage cracks happen because there is a restraint. That means the material cannot move freely, right? So we are holding it between two supports. Same in case of the brick mortar. We have a lot of cracks you will see in your brick walls. Because the mortar is restrained between the two bricks, it cannot shrink or swell, right? So we want to mitigate this shrinkage because ultimately these cracks will be the reasons for seepage and all other durability issues in buildings, right? And I won't go into this. This is how shrinkage happens, but anyway, that is not very important. So what we did is that we took 3 particle sizes of biochar, coarse, medium, fine. The reason being, when you take different particle sizes, you also get different levels of porosity. And different levels of porosity means different sort of water retention. And we measured those using a technique called mercury intrusion porosimetry, what you see here. And these are some images of these particles. And then we wanted to find out what is the change in relative humidity and the change in water absorption, desorption behavior that you have with biochar. Right? This was done using some sensors. So what you see in this case is that when you don't have biochar, your internal relative humidity, the amount of moisture contained actually drops very shortly, right, with time. But when you have pre-soaked biochar that contains water, that you saturate the biochar with moisture, you see that the drop is much less compared to that of the plain concrete, right? That means you are retaining more humidity, more moisture inside the material, which is conducive for the hydration for better strength. And why it happens is because the water that is absorbed in the biochar, which is in the first plot, is actually dissolved under a humidity gradient. Humidity changes, the water comes out of the biochar structure, right? And that prevents the loss of the reduction in the internal humidity. Right. So as a result of that, we got better hydration because of this internal curing effect. We got a better precipitation of the gel structure, right? And this is actually good for strength development as well, which is shown here. I won't go into the details anyway. Right. Yeah. So coming to the ultimate problem, there's a reduction in shrinkage. We did witness quite a bit of reduction in the total change in length, which we measure using a simple comparator, to a micron level. And we see that using biochar can mitigate the amount of shrinkage after 90 days of monitoring. And that also happens when the material is exposed to the immediate environment, when drying evaporation happens. There is a mitigation of about, more than 10% shrinkage biochar mortar. So you can prevent shrinkage cracks, early age or late age shrinkage crack using this technique. And currently we are basically looking at a way to reduce the thermal shrinkage in biochar using an activation process in mass concrete structure like dams, huge concrete structure. You have a huge temperature rise inside the material. So the surface becomes cooler, the core remains warmer, and that causes a lot of thermal shrinkage. So what we wanted to do is, by using some activation path, we wanted to mitigate the heat evolution, but still have similar or better strength at a later age. So these are some sort of alkali activation. You can later go through this. And we increase the surface area of the biochar by 8 to 10 times using, which are actually good for late age properties, right? So that's what you see here, the increased surface area from actual normal biochar to the modified biochar. Some images which shows the change of pore structure that you have. But one thing I should mention here important is that at a high temperature activation, the thickness of the pore walls become less and less. And therefore you might have some collapse around the pore walls, which may lead to more brittleness. Right? And then this is a sort of carbon uptake that again we calculated using some analytical technique. So the activated biochar gives much higher carbon uptake due to higher porosity and higher surface area. This is the most interesting part, where we saw that when we have activated biochar, we actually mitigated the early heat release, which is on the y-axis, but the ultimate heat release is actually increased after 7 days. So this heat release is actually a measure of hydration, how much of reaction is taking place inside the concrete. The higher the better it is, but not at the early stage. So it is important to mitigate the heat evolution during the early stage to prevent thermal shrinkage, but not at the cost of later age hydration. So we kind of tuned the whole process that we get better later age property than early age property, which is shown here. And this is again the last slide I think I have had. is that why this happens is because when you are activating at high temperature, you are increasing the aromaticity of biochar. It becomes more like a benzene. And this sort of biochar do not support hydration as much during the early stage. And therefore you see that some of the pores are actually not filled with hydration product because it repels water. It becomes more and more hydrophobic, right, during the early stage. But of course the surrounding is densified and therefore you have less heat of hydration because you have some vacant pores, vacant spaces in the material due to increase in the water repelling property. So in summary, biochar can be an excellent additive if you engineer it in a right manner. It can also tune the hydration kinetics, improve the stability of concrete at high temperature depending on the porosity, depending on the surface area. And finally, it can also be used as a blended admixture for reducing the content of cement and aggregate for the building materials while improving your strength, later age strength. Right? So with that, I'll stop. Any questions, you're welcome. Thanks.
Thank you, Dr. Gupta.
Long live India and France friendship.